Hey, AP Pre-Calc, this is Ms. Henry, and today we're going to look at section 2.7, which is about composition of functions. Our learning target is I can evaluate the composition of two or more functions for given values. So, if we think about the function f of x equals 2x minus 3, then when we evaluate that, remember, we're going to take the value we are given, like 5, and we are going to replace our variable with that number. And everything else will stay the same. So we'll end up with 2 times 5 minus 3. So your first step is to erase and replace. And then you will simplify using your order of operations, so GEMDAS. So we'll do our multiplication first. 2 times 5 is 10. And then 10 minus 3 means f of 5 equals 7. So we can do the same thing even if we're not given a number, like f of c. We'll still do 2 times c minus 3. And then just to simplify that, we get rid of our parentheses, so f of c is just 2c minus 3. So then if we're asked to do f of 4a, then we're going to erase x and replace it with 4a. So 2 times 4a minus 3. And then we're going to multiply first. So we get 8a minus 3, and those are not like terms, so that is our final answer. Then, when we are replacing our variable with something other than a monomial, instead of just multiplying our terms, we're going to have to end up distributing. So we get 2 times 5x minus 1 minus 3. So then when we distribute and multiply the inside of our parentheses by 2, we get 10x minus 2 minus 3. And then when we combine our like terms, we get f of 5x minus 1 equals 10x minus 5. So just simple, back to your Algebra 1 type evaluating functions for different values of the variable. So, but sometimes in math, when we substitute a value for a variable into a function and get something back, sometimes we will then take that answer and substitute it into another function. When we take that output value and put it back into another function, that is what is called a composite function. So for example, if g of x equals 3x plus 1 and g of 2 equals c, then we want to find g of c. So we start by finding g of 2, which would be 3 times 2 plus 1. Then when we multiply, we get 6 plus 1, and then 6 plus 1 means g of 2 equals 7, which implies 7 is c. So then our g of c becomes g of 7. Which would be 3 times 7 plus 1. And then we do our multiplication. 3 times 7 is 21. plus 1 means g of 7 equals 22. So another way to write this and be told to evaluate is this would be the exact same as asking for g of 2. So that would be the exact same process. And there are actually two different ways that we can write composite functions. So there's one way that kind of looks like fog. So f of g of x. And then similar to how I wrote it with g in our previous example, we could write it as f of g of x with parentheses instead of the circle. And both of those are read the exact same way, f of g of x. And it is important to note that when we are working with composite functions, we always start on the inside with what we are going to evaluate. Just like your order of operations says that you have to start inside of a group, we always evaluate the inside first, which in that case would be g of x. Then we would take the answer from g of x and substitute that in to f of x. So you're always going to work from the inside out. So we have a new function f and g. F of x is 3x minus 5, and g of x is 2x plus 1. And then we're going to evaluate three different expressions. So as we said, we always start with the inside. So we're going to do g of 3 first. So g of 3 would be 2 times 3 plus 1. Then we multiply, so 6 plus 1, which gives us 7. So we know g of 3 equals 7. So then we're going to substitute the 7 in for f. So we're going to do 3 times 7 minus 5. And then 3 times 7 would be 21. Minus 5 means f of g of 3 equals 16. So let's check it going the other way. Instead of f of g of 3, we're going to do g of f of 3. We still always start on the inside, so this time we're going to do f of 3 first, which would be 3 times 3 minus 5. 3 times 3 gives us 9. Minus 5 means f of 3 is 4. So now that we know what f of 3 is, we're going to do g of 4. So we're going to do 2 times 4 plus 1. 2 times 4 is 8, plus 1 means g of f of 3 equals 9. So notice how the order does matter. Whether f or g comes first, that does make a difference. So Now I want you guys to try f of 4. So for example 3, we're still going to be using these same functions f and g, but now we're going to create an equation for the composition of just x. So remember, we always start on the inside, but because it's just x, g of x is going to stay just as it is. So this is going to be the same as f of 2x plus 1. So then we're going to use f, and we're going to replace x with 2x plus 1. So we get 3 times 2x plus 1 minus 5. And then we will distribute the 3 into our parentheses, giving us 6x plus 3 minus 5. And then when we combine our like terms, we find that f of g of x equals 6x minus 2. So now we're going to go the opposite way. We're going to put f of x into g of x. So this would be the same as g of 3x minus 5. So we're going to take our g, which is 2x plus 1, and instead of x, we're going to put 3x minus 5, and then add 1. And we're still going to distribute first, which gives us 6x minus 10 plus 1. So then when we combine our like terms, we can see that g of f of x equals 6x minus 9. So notice how the composition is not the same when we go in different orders. So the order is very important. So now we have 4 different functions, h, k, p, and m, and we're going to do a couple different compositions. So k of h of 2, remember we're going to start inside first and find h of 2, and h is our first function. So h of 2 is 2 times 2 minus 3. 2 times 2 gives us 4, minus 3 means h of 2 equals 1. And then we're going to take that value of 1 and put it into k. And k is our second function. So we're going to get 1 squared plus 4 times 1 plus 5. And then we can do our exponents and our multiplication at the same time since they are not connected to each other. So 1 squared is just 1, 4 times 1 is 4, then bring down our plus 5. And then 1 plus 4 plus 5 means k of 1 equals 10, which means that k of h of 2 equals 10. So I want you guys to try b and do h of m of negative 1. So remember, this can be rewritten using parentheses. So you're going to find the composition of m of negative 1 and then use that value and find your function value of h. So let's look at c together. So as I said, we can rewrite this composition as k of p of x. So since we have an x in there instead of a number, we're going to replace p of x with what it equals. So we get k of the square root of 3x plus 1 So first, we're going to substitute in our radical, so 3x plus 1, and then we end up squaring that, and then plus 4 times the square root of 3x plus 1 plus 5. And then we're just going to simplify. So whenever we square a square root, they cancel each other out. So we get 3x plus 1 plus 4 square roots of 3x plus 1 plus 5. And then we can combine some like terms so that we get k of p of x equal to 3x plus 6 plus 4 square roots of 3x plus 1. So if you are not substituting in a value, then your final answer will be another function, just like we saw here. So next, we have a combination of 4 different functions. We have the graph of f of x, the table for g of x, the piecewise function of h of x, and then we're told k of x is a quadratic function, meaning it has to have x squared in it, that has a horizontal translation of 2, meaning we're going right 2, and a vertical translation of -3, which means we're going down 3. So if we think about using those transformations, we can write our function of k of x. So because we're going right 2, it's going to be x minus 2 in parentheses squared, then minus 3. So that's our function we will use for k. So starting with a, f of g of 3. So remember, we're going to start on the inside and find g of 3. And remember, g of x is our table. But if we look at where our table is, we do not have an x value of 3. So because we cannot figure out what g of 3 is, we would say it is not defined, which means our composition is also not defined. So if the value does not exist in your table or in your function, you would say not defined instead of being able to continue evaluating. So now let's look at B, h of f of 8. So we're going to start with f of 8. And f is our graph, so we look at where x is 8, and we can see our point is at 8, -1. So f of 8 equals -1. So then I'm going to do h of -1 which would be our piecewise function. And because -1 is less than 1, we're going to use our first piece to evaluate this. So we have the absolute value of -7 plus 3 times x, which is -1. So we're going to do our multiplication first. So we get -7 minus 3. -7 minus 3 is -10. And then the absolute value of -10 is +10. So we get h of f of 8 equals 10. So next we're going to take a look at g of k of 0. So remember, we move backwards, whether it's inside out or just moving from right to left, doing k of 0 first. K is our quadratic, so we're going to use our transformed quadratic. We have 0 minus 2 squared minus 3. So 0 minus 2 would be -2 squared minus 3. -2 squared is 4. Minus 3 gives us 1. So then next, I'm going to do g of 1. And g, once again, is our table, but we do not have an x value of +1, so once again, this would be not defined. And our composition would also be not defined. So the way we would know if something was in our table is, say it was g of -1, then your bottom row, your y value, would be your answer. But because we don't have a +1 as an x value, we're not going to be able to evaluate that. So let's do one more together, f of 2. So we're going to start inside with f of 2. And remember, f is our graph, so we're going to look at an x value of 2. We ignore any holes. You have to look at your actual point. So f of 2 is 1, because that is the only point that actually exists where x is 2. So then we're going to do f of 1. So we're going to go back to our graph, and where we have an x value of 1, we have a y value of 4. So f of 1 equals 4. Which then also means f of 2 equals 4. Then I want you guys to see if you can get E and F, and we'll chat about them next time I see you in class. Talk to you guys later.